In the late evening of the 1st of January and the early hours of the 2nd of January, 2019, the container vessel MSC Zoe experienced a major cargo incident while transiting the North Sea. During the passage through the Terschelling, German Bight traffic separation scheme, the vessel lost a large number of containers overboard. MSC Zoe, a Panama-flagged ultra-large container ship, was en route from Sines, Portugal, to Bremerhaven, Germany. At the time of the incident, the vessel was operating in severe but forecasted weather conditions, with strong north-northwesterly winds and waves approaching from the port side, causing continuous rolling. The first indication of container loss was detected shortly after 1 o'clock local time on the 2nd of January. Around 1:30, further container losses were directly observed by the crew. In response, the vessel altered course and reduced speed to stabilize its motion and informed the relevant vessel traffic service authorities. After the incident, MSC Zoe continued towards Bremerhaven and berthed safely on the 3rd of January, 2019. No injuries to crew members were reported, and the vessel remained fully operational. Due to the scale of the cargo loss and its location close to the Dutch and German coastlines, the accident attracted immediate public attention and led to a formal international safety investigation. The purpose of the investigation was to determine how and why the container loss occurred, and what lessons could be learned to prevent similar accidents in the future. Following the accident on 1 to 2 January 2019, a formal safety investigation was initiated. On the 6th of January, 2019, investigators from the Maritime Safety Authorities of Panama, Germany, and the Netherlands boarded MSC Zoe in Bremerhaven and formally started the investigation. The investigation included onboard inspections, examination of damaged cargo securing equipment, collection and analysis of voyage data recorder data, loading and lashing calculations, weather and sea condition assessments, and evaluation of the environmental impact of the lost containers. Further technical analysis, simulations, and coordination meetings between the investigating authorities continued in the following months. The investigation commission concluded that the accident had serious and far-reaching consequences, affecting the cargo, the vessel, the cargo securing system, the crew, and the marine environment. As a result of the accident, 342 containers were lost overboard, primarily from bays 10, 26, and 58. The losses occurred during at least 6 separate events, rather than a single incident. Several container stacks collapsed on deck before falling overboard, while others were lost directly into the sea during periods of violent rolling. A large number of containers were destroyed after falling from height into the water. Their contents were released and transported by wind, waves, and currents. Cargo debris washed ashore along the Dutch and German coastlines, including the Wadden Islands. The pollution affected a particularly sensitive marine area and required extensive shoreline cleanup operations. The investigation confirmed that 2 containers carrying dangerous cargo were lost at sea. A third dangerous cargo container was found partially hanging overboard and had to be handled with extreme caution. Although no bunker fuel or lubricants were released from the vessel, the environmental impact of the lost cargo itself was considered severe. The vessel did not suffer critical damage to its hull or propulsion system. Inspections did not reveal grounding damage to the bottom or bilge areas. However, the ship sustained extensive damage to the cargo securing system, which was one of the most significant technical consequences of the accident. Detailed inspections showed that the lashing system failed progressively, not as a single sudden failure. Numerous lashing rods were found broken, bent, or permanently deformed. Many turnbuckles were overstressed, locking pins and hooks were missing, and a large number of twist locks were fractured, in some cases broken completely in two. Once the first lashings failed, the loads acting on the remaining securing elements increased rapidly. This redistribution of forces caused subsequent lashing failures, leading to the collapse of entire container stacks. In several locations, containers were left hanging overboard, creating an immediate and serious safety hazard for the crew. Collapsed stacks, loose containers, and damaged lashing equipment rendered large areas of the deck inaccessible. The condition of the securing system also meant that further container losses could not be ruled out during the night. For the crew, the situation was extremely dangerous and highly restrictive. Severe rolling, darkness, loose cargo, and damaged securing gear prevented safe access to the deck. As a result, damage assessment during the night was very limited. Importantly, the first container losses were not detected, eliminating the possibility of early mitigating actions, such as additional course or speed changes, that might have reduced further losses. The Investigation Commission concluded that the loss of containers from MSC Zoe was not caused by a single failure, incorrect decision, or human error, but by a complex interaction of design, operational, environmental, and regulatory factors. A key factor was the size and stability characteristics of the vessel. MSC Zoe is an ultra-large container ship, approximately 400 meters long, with a beam of 59 meters and a theoretical capacity exceeding 19,000 TEU. At the time of the accident, the vessel was operating with a corrected GM of about 9.0 meters, a value typical for ships of this size. High GM resulted in short natural roll periods, bringing the vessel close to resonance with the dominant wave periods north of the Wadden Islands. This caused the ship to respond violently to beam seas, generating very high transverse accelerations, even though the geometric roll angles remained moderate. The investigation emphasized that high stability must be regarded as a risk factor, not a safety margin. Current international stability regulations focus almost exclusively on minimum GM values and do not address the dangers associated with excessive stability on large and wide container ships. Cargo configuration further increased vulnerability. Heavy containers were stacked to considerable heights on deck. During rolling, these tall stacks generated large overturning moments and leverage forces in the lashing system. Once the first lashings failed, loads were redistributed, resulting in progressive collapse, first in Bay 26 and later in Bays 10 and 58. Cargo securing was carried out in accordance with the Cargo Securing Manual, and the loading computer indicated compliance with allowable limits. However, the investigation found that the calculation models did not adequately account for short-duration extreme accelerations, impulsive loads from slamming, green water on deck, and shallow water effects. A critical finding concerned under-keel clearance in dynamic conditions. The investigation did not identify a draft planning error. The vessel complied with static under-keel clearance requirements and was legally afloat. However, the investigation identified a passage planning weakness under the prevailing environmental conditions. In shallow water, the combined effects of high stability, beam seas, vertical ship motions, and wave grouping significantly reduced the dynamic under-keel clearance. Model tests demonstrated that during groups of high waves, the vessel experienced large vertical motions combined with rolling, making contact or near contact with the seabed possible. While no bottom damage was detected, soft contact with the sandy seabed cannot be ruled out and would have generated impulsive loads and vibrations transmitted throughout the ship's structure. Environmental conditions were severe but not exceptional for the North Sea. Significant wave heights increased from approximately 5.0 meters to 6.5 meters, with individual waves potentially reaching around 11 meters. In combination with shallow water effects, these conditions produced short, violent rolling events and extreme accelerations. Situational awareness on the bridge was limited. Mechanical inclinometers indicated roll angles of up to 30 degrees, which the crew reasonably interpreted as actual heel. The investigation determined that the true roll angle was approximately 16 degrees. Mechanical inclinometers are gravity-based instruments and are highly sensitive to accelerations, leading to overestimation of roll angles in dynamic conditions. This meant that the vessel was not rolling to extreme geometric angles, but was experiencing very high accelerations at relatively moderate roll angles. From a cargo safety perspective, accelerations are far more critical than roll angles alone. The crew had no instruments capable of displaying real-time accelerations or dynamic loads, leaving them unable to assess how close the vessel was operating to the physical limits of the cargo securing system. Finally, although legally permitted, routing and timing placed the vessel in sustained beam seas in shallow water at a critical stage of the voyage, increasing exposure to resonant rolling and extreme accelerations. The investigation concluded that the accident exposed a systemic gap between the physical behavior of ultra-large container ships, the assumptions embedded in cargo securing standards, and the operational tools available to crews. Following the accident on board MSC Zoe, search and recovery operations were initiated, but only a limited number of containers could be recovered due to water depth, strong currents, and the damaged condition of the cargo. Beyond the immediate response, the investigation concluded that existing cargo securing standards and calculation models were not fully suited to ultra-large container ships operating in severe weather and shallow water conditions. It recommended revising these models to better reflect real ship behavior, including extreme accelerations, impulsive loads, and shallow water effects. Further recommendations included improved passage planning and weather routing, recognition of high GM as a risk factor, improved bridge instrumentation beyond mechanical inclinometers, and greater transparency of loading computer and lashing software calculations. The investigation also identified limitations in the traffic management framework in the German Bight. While Master of Science Zoe was legally allowed to use the southern route, the accident demonstrated that legal compliance alone was not sufficient to manage the actual risk. As a result, traffic management practices were adjusted, with a stronger preference for northern routes in the German Bight for large container ships during adverse weather conditions. These measures were introduced as risk-based guidance, not as a formal ban. The MSC Zoe accident showed that safe operation of modern container ships requires more than compliance with existing rules. Safety depends on aligning ship design, cargo securing, route planning, and traffic management with the dynamic realities of ship behavior at sea.